Welcome to The Explainer. Today, we are demystifying the mathematics of change by tackling a concept that, let's be honest, sounds a bit intimidating at first, but is actually incredibly intuitive. We're talking about integrals. If you've ever wondered how scientists, engineers, and mathematicians measure the accumulation of things over time, you are in the exact right place. Let's break it all down. All right, let's kick things off with a pretty common puzzle. Imagine you only know how fast water is flowing out of a pipe. How in the world do you figure out how much water is actually sitting inside the tank? In real life, we don't always have a neat little gauge telling us the total volume or distance. A lot of the time, all we have is the rate of change. So we have to somehow piece together the total amount just from the speed at which it's happening. Your car's dashboard brilliantly illustrates this concept using something we see every single day. While your speedometer is showing your current rate, your exact speed right at this very second, the odometer is quietly doing something else. It's accumulating all those speed values over time to give you the total distance you've traveled. In math terms, the odometer is literally performing an integration of your speed.
Let's visualize some real-world flow with a propane tank.
Picture a building drawing heating fuel from a big propane tank. Now, suppose this tank doesn't have a physical level indicator. To know how much fuel is left, we've got to rely on a flow meter installed directly on the gas pipe. This meter measures the flow rate, how much mass passes through per hour, for example. By taking that average rate and multiplying it by the time that's passed, boom, we can indirectly figure out the total consumed mass. But real life is rarely that tidy, right? What if the flow rate isn't perfectly constant? What if the appliances in the building are turning on and off? Well, if the flow rate changes over time, we can approximate the total propane used by treating each period of constant flow as its own wide rectangle. The width is the time interval, and the height is the flow rate. By summing up all those blocky slices of area, we get a really solid approximation of our total mass used. Now, actual flow rates change continuously. They don't just jump up and down in chunky, awkward stair steps. So as we use narrower rectangular slices to track that flow rate over much shorter time intervals, our approximation of the area under the curve gets significantly better. And here is the real aha moment. By shrinking those slices down to their ultimate limit, an infinitesimal width, meaning they're practically approaching zero, we get a perfectly smooth, exact representation of the area under the curve. We aren't just approximating anymore. This continuous summation of infinitely tiny slices is the absolute essence of integration. Moving right along, let's demystify the notation.
Okay, be honest, you've probably seen this symbol before and thought, yikes, but it's really nothing to be scared of. It's literally just a stretched out, stylish letter S. It stands for sum. It's just a symbol telling us that we are continually summing up all those tiny, infinitesimal slices we just visualized with the propane tank. That's it.
And when you see dx hanging out at the end of the math expression, it simply means that those slices, let's say of time or distance along the x-axis, are shrinking down to approach a width of zero. That little d just signifies that infinitely small difference in width.
Next up, the reverse derivative.
Think back to a tap in a tank. If a tank's volume is increasing at an accelerating rate of x squared, taking the derivative tells us the actual flow rate into the tank is 2x. But it works in reverse. If we start out knowing the flow rate is 2x, the integral works backwards to tell us the accumulated volume is x squared. They're completely intertwined, two-way operations.
Let's look at definite versus indefinite integrals. So what's the actual difference here? Well, think of a definite integral like a road trip with very clear start and end flags. It gives us exact numerical quantities between specific boundaries, like calculating the exact miles you drove strictly between hours 2 and 4 of a trip. You'll see little letters, usually A and B, at the top and bottom of the S symbol to indicate those bounds. Indefinite integrals, on the other hand, are more like an endless open road. They don't have boundaries. They simply provide the general formula, or what we call the antiderivative, for the function itself. Now, with indefinite integrals, you're going to run into a funny little quirk called the constant of integration, or simply plus c. Think about it. If you are measuring the flow rate of water into a tank to find the total volume, the math alone has no way of knowing if the tank started out empty, half full, or completely full before you even turned on the tap. Because the derivative of a constant starting amount is always zero, when we run the process in reverse and integrate, we have to add that plus c. It accounts for whatever volume might have already been hanging out in the tank. Finally, let's talk about the rules of the integration game. Just like with derivatives, we've got some standard rules you can memorize so you aren't calculating infinite slices from scratch every single time. For power functions, we use the power rule. You just add 1 to the exponent and divide the whole thing by that new number. For exponential functions, and this is actually really cool, e to the power of x is its own integral. And of course, we have cyclical rules for trigonometric functions, where the integral of cosine x, for example, is simply sine x plus c. What's really nice is that integrals politely obey basic algebraic rules. The integral of a complex sum is just the sum of the individual integrals. This means you can break complex functions apart into manageable sums and differences, and you can even grab constant multipliers and pull them right out to the front of the integral symbol. It makes the math significantly easier to handle.
But what about those trickier problems that just look like a tangled mess? For those, we use a method called substitution. Think of this as a reverse chain rule. You identify an inner piece of a complex equation, swap it out for a simple variable called u, make sure its derivative is present, simplify the integral, solve it, and then plug your original x values right back in. It is a remarkably elegant way to untangle messy equations.
We've seen how integrating infinite, tiny slices reveals the whole picture, whether we're talking about distance, mass, or volume. Calculus is, at its core, the study of how things change and accumulate. So as we wrap up this explainer, look around you and ask yourself, what invisible flow rates in your own life are just waiting to be summed up